Good day, everybody. Great to see you. Since Lynn's already sharing her screen and ready to go, I won't uh, kind of change the slides and put up mine, but let me just remind us all about sort of what we're here today to do. So I'll read the slides in front of me, even though you guys can't see them. That is, we are the Process Studies and Model Improvement Panel here at US CLIVAR. The goal of US CLIVAR is to foster understanding and prediction of climate variability on a range of timescales. Uh, to serve the climate community and society through both the coordination and facilitation of research on really outstanding climate questions, and particularly as it pertains to the role of the ocean in some of these science questions. Our specific mission as the Process Study Model Improvement Panel is to reduce uncertainties in general circulation models that are used for climate variability prediction and climate change projections. And in doing this, part of our work is to review, prioritize, and coordinate relevant process studies, climate process teams, advise US CLIVAR on research priorities, develop and encourage mechanisms such as community workshops and studies and working groups in order to help our group reach our goal and to help US CLIVAR. And part of that, our work is in reviewing and learning from different field process studies that are ongoing. And that's what we're going to hear from today with Lynn McMurdie and the impacts. Let me change my screen. So Lynn is a research associate professor at the University of Washington in the Department of Atmospheric Science. That's where she got her PhD from in 1989. She has a number of awards, including several teaching awards, and also has been a part of other field campaigns previously. Her focus areas have been on synoptic and mesoscale structure, the dynamics and microphysics of mid-latitude cyclones, including banded precipitation structures in developing storms, and especially in snowstorms over the East Coast. And I believe that's what we're going to hear a lot about today. So if there's anything I've left out there, Lynn, that you'd like to add, please
No.
feel free to do that. But otherwise, the floor is yours.
Thank you so much for that great introduction. That's exactly what I'm doing right now. And I am here to talk about an ongoing field campaign that we have called Impacts, Investigation of Microphysics and Precipitation in Atlantic Coast-Threatening Snowstorms. And I just want to give a shout out here to my deputy PI. So I'm the principal investigator for this project. It's a fairly large one, and but I work very closely with Jerry Heimsfield, John Yorks, and Scott Brown, all at NASA Goddard. And it goes forward here. So for those of you who live on the East Coast know well, snowstorms can be very picturesque with all the beautiful snow on your trees, but they also are hazardous. And this is just a bunch of headlines from an event that happened this last winter that we did sample of a blizzard that occurred over the eastern seaboard, mainly in the Boston area. So because of their hazardous and impacts to power and transportation and general society, it's important to understand the processes that are going on in these snowstorms, especially the precipitation. So what's interesting about snowstorms, they have a whole variety of intensity. Some are really strong, like this event that I just highlighted, and this is a satellite picture of it here with the low pressure center here. And others are fairly weak, but they still produce snowfall and have an impact. What's also interesting is not only the storms vary, but the snowfall within them varies very strongly. And you can almost see that here from the satellite pictures that I have for this event. The clouds features span from way up in Newfoundland all the way down to South Carolina and probably down into Florida here. But there's a lot of structure inside of them. You see lots of a very fine scale, a larger scale, and actually most of the snowfall is back in here over the Boston and New York area. And if you go on closer, you can see that there's all kinds of structure, and often the structure is in these narrow banded structures. We call them snow bands that are highlighted here on the right-hand figure, which is a radar reflectivity picture from the Boston, operational radar. So these regions of higher reflectivity are correlated with snowfall at the ground. And each of those bands come through and they can produced quite a bit of snow. And what happened in this last event, Plymouth, Boston, Massachusetts got hammered with over 2 feet of snow from multiple bands going over them over and over again. The IMPACTS is a NASA-funded Earth Venture Suborbital, that's what the EVS-3 stands for, field campaign to study East Coast snowstorms. Earth Venture Suborbital means using aircraft as opposed to satellites to lead the field campaigns. Past work on snow bands and snowstorms really used models and ground-based radars only, and they focused on just the primary band because that's really what you could observe with just a ground-based observational platforms. But there's a multiple scales of banded structures. You have this broad one here, as you can see in my figure on the left, but there's lots of little ones. And our questions are, what are the causes of these banded structures? And if we understand the processes that go in them, can we predict them better? And can we measure them in space better? Here's some pictures from the field here. There hasn't been a major field campaign on the East Coast focusing on snowstorms in over 30 years. It's been quite a long time. Because there's a lot of new advances in instrumentation and numerical models, it's really a ripe time to perform this investigation. So our science goals are summarized in this figure with the background of a very intense snowstorm that occurred in 2018. We want to characterize the spatial and temporal scales of these banded structures shown here in radar, understand their dynamics and thermodynamics, the processes in the atmosphere, and also the microphysics processes that's down to the scale of the cloud particles themselves that fall out to eventually become snowfall on the ground, and apply that information to better do remote sensing of snowfall and better modeling. So these are our overall goals of this campaign. I thought you might be interested to know of my science team, and I'm I'm hoping I didn't forget anybody important because it's a fairly large science team. We have many university participants. I just listed the PIs here of several institutions that I'm working with closely, and I work very closely with several NASA centers, especially Goddard, Marshall Space Flight Center, Langley, and Ames. And the National Weather Service and Weather Prediction Center are very key participants. Dave Novak did some of the early studies of snow bands, and Jeff Wallstreicher is our key liaison because the Weather Service worked very closely with us during operations, providing additional sounding and forecasting support, and enabled our student forecasters to work one-on-one with operational forecasters to predict whether or not we should go fly or not. So other collaborative groups that aren't funded by impacts but also participated include the State University. I wrote Stony Brook and I meant to say Albany. I'm sorry, Justin, you'll never forgive me for that. Wintry Mix was a field campaign that occurred in 2022. We collaborated with them, Millersville University. We did provide some funding for them to provide us with soundings, NASA JPL, and the Global Precipitation Measurement, or GPM, satellite ground validation team led by Dave Wolf provided some ground observations. I'll talk about the aircraft here in the next slide. So our main mode of observational strategy for this field campaign is to have 2 aircraft. One of them flies fairly high, up at 20 kilometers. This is well above the snowstorms and up above in the stratosphere. And it's equipped with instruments that are just like what we have on satellites. We call it our satellite simulating aircraft, and it has a suite of radars and passive microwave radiometers. The radars are listed in green here, and passive radiometers are these 2 light blue. This is their acronyms, and the XRAD is also a radar. We do also have a LiDAR instrument and lightning detection instrumentation on the ER2, and it can fly above the snowstorms. And the benefit of that is that unlike a satellite, which you don't have any control over, it just flies over your storm or misses your storm entirely. With ER2, we can tell it exactly where to go and go back and forth over and over and over again over the storm. Underneath, in coordination as best we can, it's hard because the two aircraft fly at different speeds. The P3 is instrumented with microphysics instrumentation and has flight level environmental measurements. And whenever it's over the ocean, they do dropsondes. That's getting the vertical profile of temperature and humidity and winds. And we're allowed to do that over the ocean. On the ground, we did have 2 mobile radars and a fixed radar site in that ground validation site provided by the GPM group, and 3 mobile sounding teams. Most of our radars are at Stony Brook, and the sounding teams are mobile. They'll go to where the storms occur. And we also use New York Mesonet observations and the Weather Service observations. Some of these figures are, I'm just highlighting, are already up on an early online release of a BAMS article about impacts, and I have the full DOI here, which I can share with you later if you want. Just so you have a feel for these storm systems, this is a schematic of a typical mature mid-latitude cyclone as seen from space, and this is an outline of the clouds. The regions that exhibit these banded structures of snowfall are mostly to the northwest of the surface low pressure center or to the northeast here. So these are the 2 primary regions that we are sampling, but doesn't mean we don't go other places. Rarely in this warm sector because it's generally too warm, but in the southwest sector of the low, near the low, you can see banded structures. Far away, it tends to be too dry. So this is gives you an idea. Although in our title we have Atlantic coast threatening snowstorms, we do also fly in storms over the Midwest, because if they're happening there, we're going to go. So we aren't tied to our ground instrumentation at Stony Brook, but we take advantage when the storms occur there. But if they're not, we'll go somewhere else. Our 2 aircraft are housed at different airports. P3 is at the Wallops Flight Facility. In the ER2, we negotiate a location. In 2020, we were at Hunter, which was near Savannah, Georgia, and last year we were at Pope in North Carolina. These are range rings that show that we could get to these 2 locations fairly easily. It was nice to be in North Carolina because we could get up into Canada. However, the winds at Pope sometimes made it so that ER2 couldn't get off the ground. So we've had 2 deployments so far. A third is planned for next winter. I'm hoping it will be January 6th through February 28th. So we have 7 to 8 weeks of potential flights. These are the flight tracks from the 2 different deployments we've done so far. 2020 wasn't the greatest weather year. It was a bit warm. And we went to the Midwest a couple times. We were up in the Northeast, did some calibration flights and also a GPM overpass off of North Carolina here. 2022 was a more typical year. We had 11 science flights. We targeted GPM overpasses and Midwest and East Coast cyclones. We had a nor'easter, strong funnel bands, and a couple Alberta clippers that were up in Canada. So we sampled all kinds of a variety of storms. Just to give you an idea of what it's like to be in the field, this is sort of a timeline. We have daily briefings, and usually about 3 days out, we have identified based on forecast models that there's a snowfall event, and they could be any kind. And we start drawing flight regions of interest to fly in. This is example what we did for that 29th of January 22 case. We said, we're going to fly somewhere around here. And then by 48 hours, we are notified air traffic control, requested any kind of warning areas, and final plans are submitted 24 hours in advance. And then during the flight, we actually make adjustments in real time. We are adjusting the flight levels. We communicate directly with the pilots in real time. It's kind of quite intense at times. And so these are what we submitted for flight plans, and this is what we really did. So it's pretty different. And that's just as we watch the snow clouds go through, and this is how we adjust. I thought I'd show you a few results and then talk about modeling, because that was requested for me to highlight what our science efforts have been so far with that. And since I used this January 29th case as an example, I repeated this slide here. And there's shows you how the storm evolved here from the satellite perspective. I lost my cursor again. There it is. Storm was offshore and deepened rapidly. And this is what our nemesis is, this area where the drying of the clouds occurs. You have to watch out for that. But we were flying right over the Boston and Maine area at that time. I thought I'd show you some of our soundings from this event. The little stars here are where we had our mobile teams, and these is where we made drop sondes over the ocean. And this is actual profiles to show how very, very cold it was at the surface, a very strong inversion with warm advection over the top, which was true in every location. We saw that same structure. Here's a deepening storm, very strong winds here. And one note I put here, at the time, the last two deployments, we just did our drops, our soundings, and posted these images as they happen in real time, but we did not upload the data to input for model initialization. And I'm interested in doing that for 2023 so that the data that we're collecting in real time could be useful for operations, not only for nowcasting, but for model forecasts for future events, so to help the whole modeling operational data assimilation issues. So I'm looking into how to do that. Just for fun, here is a radar image of that nor'easter and the red arrows where we flew. And these are images of the cloud particles that we collected along that flight height, which was about 3 kilometers, 10,000 feet. What's interesting is on the portions that are in the western portion, our beautiful snowflakes are pretty pristine. Sometimes they get to be these very large clusters and really interesting shapes. And on the right-hand side, or to the east, nearer the low, you can see these crystals have little dots on them. That's super cool liquid water adhering to the crystals as the crystals are falling through a region of super cool water that's been lofted up from strong vertical motions. These timelines of the blue lines are estimated liquid water content, and to the west it's very low, thus it's pristine and mostly ice, and to the east it's much higher with spikes. And that's an interesting aspect to these banded structures that we're investigating further. Another pass later, the poor guys on the P3, this was literally a roller coaster ride. These are turrets that go up to about 6 to 8 kilometers of strong upward motion and high reflectivity. They were going in and out of them. And apparently the scientists on board were calling this worse than a Six Flags roller coaster ride. Can you please get us out of here fast? So it was kind of an interesting ride, but you can see again these super cool water, and even one of our probes measured only droplets, and that usually is an indication of very strong vertical motion, and that's at bringing the super cool water up to temperatures of -16. So that was an intense storm. I also wanted to show you some early results from the 2020 period. This is a little more mature since we've had a couple years to analyze this data. This is a loop of radar reflectivity with our flight tracks on top. And you can see this region of high reflectivity kind of parked over upstate New York. The parts that are grayed out are regions where it's probably raining at the surface, and the bright band part where snowflakes start coming falling through warmer temperatures and start melting. The radar interprets that as a very large raindrop, and so they look really bright on radar reflectivity. And you can mistakenly think like, oh, it must be snowing really heavily, but it's actually the bright band. So we mask that out. So here it is when it's not masked out, so you can see it looks really bright, but that's actually snow. This is the path of the the P3 at certain times. And this region here is actually a region of more intense snowfall or snow band. It doesn't really be classified as a band because it's not very narrow, but it's still of interest to examine. So this is looking downwards from the ER2 with the X band radar reflectivity. And I'm just highlighting this one little box here. It's red. higher reflectivity here. And that is correlated with the region of vertical motion. And we detected that from the Doppler velocities from the radar. And so that snowband or banded region of higher snowfall at the surface is related to vertical motion. And another technique we use, which will relate to remote sensing, is looking at the dual frequency ratio between two radar bands, so the Ka and Ku, and when that is higher, so this is a high dual frequency ratio value, and we looked at the microphysics within that box, and we see that the mean diameter, which is what's plotted in the black line here, is larger in the dual frequency ratio higher. And when you look at the probes, and yes, those are bigger particles, mostly aggregates. So the higher values means it's aggregating. And when you're outside of that region, this is low DFR, they're much smaller. What's useful, why this is a useful thing to examine, is that this is something our remote sensing instrument on satellites has a radar in the Ka and the Ku band. If we can use those radar reflectivities to infer microphysics, and it's a very useful technique to retrieve the properties of the cloud. So having this co-located radar and microphysics enables us to do that. So this is part of the ongoing research. And this is doing all the flights from the 2020. The things that to point out here, so the box and whisker plots that are solid are in regions of high dual frequency ratio, and the dashed are in low dual frequency ratio. And these three events at the end were all snow events. And we see that enhanced DFR has larger particle size, smaller density, so they're more aggregates, so there's like air spaces in between, smaller number of them because they've all aggregated, and not an appreciable difference in ice water content, which is sort of interesting. It's like the same amount of moisture, but it's all rearranged itself into bigger particles. That's what we hope to repeat this analysis for the 2022, because we'll have a lot more events to see if these conclusions hold. So for the modeling efforts, I tapped into my colleagues at Stony Brook and Penn State, and they provided me with some figures here. I hope I do them justice. And the Penn State, I just actually copied in the slides that they produced for me. I just wanted to summarize the different modeling efforts here, where many groups, not just ourselves and SVU, are using high resolution the Weather Research Forecast Model, or WRF, runs, and to explore particular events and to explore the processes that may be contributing to the snow bands. The Penn State group is doing some data assimilation experiments. I'll talk about that in a minute. And we are also comparing model and measured microphysics, since we have measurements from the P3, to see how well the microphysics schemes are doing. I consider retrievals of microphysical properties to be a modeling type of experiments as well. And my postdoc is examining this, starting with that DFR stuff I just showed you a minute ago. And I believe my colleagues at Goddard are looking to improve satellite retrievals of frozen precipitation over land and over ocean. And there may be more that I'm not aware of. So just to highlight that February 7th case from 2020, my colleagues at Stony Brook have done nested gridded model experiments for that. They're exploring the processes that led to the snowfall in Western New York, and why this event didn't really have a narrow band, but a broader region. So they're using the model to explore those questions. They did multiple runs, changing the initial conditions and the microphysics schemes. And this is a comparison on the left of what we measured from that ER2 aircraft. And this was the model of simulated reflectivity, not bad, but there's probably some errors in position from the model. And you can see like it doesn't have any reflectivity in a region that there really was one. So I think that's a timing issue in this particular simulation. This is a very busy graph, but the black heavy lines are estimated rhyming fraction. Rhyming is that super cool water adhering to frozen particles. So that's amount of rhyming. An important factor, I think, in these snow bands is how much is the degree of rhyming. So that's something we could measure from the aircraft. But the model also produces those estimates in each of these separate runs using different initial conditions and different microphysics schemes has a very different idea of what the rhyming is. So this is one of the values of having these direct measurements. For example, the Thomson scheme really struggled and did not produce much rhyming. That's these two figures down here, two lines at the bottom. Here's where the aircraft, but another one like way overdid it. So we're examining why that is, what's going on in these microphysics schemes that is underestimating or overestimating the rhyming fraction. Also, there's some, I probably forgot to mention in my list, there's some, two groups are doing some idealized modeling. And my colleague, Brian Colley, and his postdoc are interested in these narrow, smaller scale banded structures. See where this yellow line is? There's very fine scale. He calls these multibands. And when you do a cross section through them, they look like these small little turrets. What are the processes going on there? So they've successfully simulated that with an idealized baroclinic model using a wharf run kind of anchored on the low, and they are inside or near the low center themselves. These are just things that he provided me, and I'm not sure if I'm going to interpret them correctly, but I think his idealized simulation actually does reproduce those multibands well. They seem to be in regions of potential instability and kind of wave-like features on some stable areas. So I'll find out more from him later, but he gave me these model runs. Lastly, I'm just going to kind of run through what the Penn State group is working on. They are focused on data assimilation efforts. They use their own WRF ensemble common filter model to and data assimilation system. They can ingest standard observations such as surface and upper air and GOES 16 satellite radiances, as well as they want to experiment simulating the impacts field measurements. They are going to conduct a series of parameter estimation experiments, and they are using this Center for Advanced Data Simulation Predictability Techniques, originally spearheaded by Dr. Fujing Sheng, who sadly passed away at the beginning of this project. He was one of our key PIs, and Matt Cumgen and Steve Raybush have taken over for that. Here's a list of some of their WRF simulations experiments. They're going to do some ensembles of between 30 and 60 members over this particular region. They've done some simulations for that same event in February of 2020 and doing fairly well. I think they have stated that it compares, they've already done a simulation of the conventional observations and the simulated composite reflectivity, and it does fairly well. So they are experimenting further, exploring why it does well, and they will do additional simulations. Here they provided a comparison of the scanning. One of our radars on the ER2 does do conical scanning, so you can see the reflectivity across a narrow swath. Compared that to the NextRad and their simulations. So they do have little underestimation of the western portion of that. So they're exploring why that is. Here's a list of their data simulation experiments that they're going through. And their next steps is to select some more cases from 2022 and explore assimilating dual pole information as well. In summary, we are a EVS3 field campaign to document East Coast snowstorms, and we want to characterize and understand snowband variability, apply this knowledge to improve remote sensing of snowfall and modeling. I didn't spend time to explain why remote sensing needs improvement. Snowfall is very difficult to do from space, largely because of the irregular shapes of the snow particles, which wreaks havoc on any retrieval algorithm. We flew multiple storm events in 2020 and 2022, all kinds of storms. There's ongoing data analysis and modeling efforts. We'll have another deployment, so we'll have more events. Most, if not all, the data sets from the 2020 field campaign are publicly available on the NASA hosted DAC. I forget what that stands for. Here's the link, how to get to it. I do want to point out, we highly encourage collaborators of all kinds, outside users to our data. We actually have a data workshop for outside users to explain more clearly what data we have, how one might use them, introduce you to our instrument PIs if you have questions. So we're very, very looking forward to doing that. And maybe people listening onto this call may want to jump on the bandwagon and check out our data. We are in the process of posting the 2022 data. That won't be available till September. But we do have quick look imagery, reports, supporting maps, everything from our field in both from the 2022 and 2020. There's 2 field catalogs also publicly available to anybody. And I think all I have at the last year is a big thank you. This is our lovely mask that we had to wear in 2022. We're in front of the P3. This is the team who was in the field on the last day of operations. A small group who are there, but we are actually a very big team. We just have people cycle through. Again, I have our data online, the DOI here for that. Here's my email. And I'm really thrilled to answer any questions you all might have. So thank you very much.